Welcome. Let's solve some trigonometric equations here. We're going to work under the assumption that I'm working under the assumption you know some basic trig identities, and we're just going to talk about some strategies toward solving these equations, whether it be one revolution worth of solutions or an infinite number of solutions. So let's get started. Okay, in this case, we just have a single trig function sine of x, so we're going to isolate sine of x. And I get sine of x equals, to isolate sine of x, I will have had to have subtracted 1 and then divided by square root of 2. And here's a graph of sine of x that we should all at this point be familiar with. And we see that sine of x, of course, goes backwards as well, and on and on and on. If sine of x hits negative 1 on root 2, which I would suggest it would somewhere around in here, it's going to hit it again and again and again, an infinite number of times. So we have to find a way to represent that. So let's take a look at a graph, rotational graph here. Sine is the ratio of y on r. So I need y on r to be in ratio negative 1 to root 2. Well, that happens when y is negative. And for instance, looks something like this, negative 1 to root 2, or negative 1 to root 2 here. And a quick Pythagorean, or we might recognize this as special 45-45 triangles. This would be negative 1 and 1, giving us this 45-degree angle. Now, if we were only responsible for solutions between 0 and 2 pi, we could handle this pretty easily. But right now, we could get to, for instance, this point by rotating 5 pi, and then we could spin around 2 more times and land on it again, or spin backwards 3 times and land on it again, or spin forward 100 times and land on it again. We have to be able to represent that. So I'm going to say that, yes, x could be 5/4 pi. Yes, x could be, to get around to here, 7/4 pi. And again, if this said solve for 0 is less than or equal to x is less than 2 pi, those would be my only 2 solutions. Those would be solutions that would lie right in here, those 2 guys. But we need to add multiple revolutions onto this. Well, if a revolution is 2 pi, a multiple revolution would be 2 pi times n. If n is an integer. Whoops, spell that right. Try that one more time here. I'm a math guy. Is an integer. So if n happened to be negative 4, then I'd be starting at 5/4 pi and adding negative 4 full rotations. So I would be starting here and spinning around 1, 2, 3, 4 times, but I still end at that point. So when I write this all the time, but I'm always in my head at the very minimum saying multiple revolutions, multiple revolutions. So there are all of our solutions. That would pick up these guys up here, and on and on and on. So that's strategy for handling that. We're going to be talking in terms of multiple revolutions. Soon we're going to be talking maybe in terms of multiple 1/3 revolutions. Okay, so another problem here. We're going to isolate cotangent. I would start perhaps maybe by saying cotangent squared of x equals, I need to add 1 and divide 3. And then to get cotangent alone, careful here, cotangent of x equals, take the square root of both sides. But if I had x squared equals 9, I hope you would say that, oh, that means x equals plus or minus 3. So cotangent of x equals plus or minus square root of 1 on square root of 3. Okay, let's take a look where that happens rotationally. That would be an x on r ratio, because cotangent it's not x on r. Cotangent, excuse me, is x on y. an x on y ratio of 1 to root 3, relatively short x compared to y. So something maybe like this, 1 to root 3. It could be over here, negative 1 to root 3, negative 1 to negative root 3, or 1 to negative root 3. Any of those locations are good values for x. So x could be, this being a 60-degree angle, pi on 3, 1/3, 2/3 pi. X could be 2/3 pi. 3/3 nope, but 4/3 yes. X could be 4/3 pi, or x could be 5/3 pi. Okay, now I could just say those are my solutions plus multiple revolutions. 2 pi n or 2n pi, multiple revolutions. But I also have an option here if I notice. I go from 1/3 pi to 2/3 pi. I skip 3/3 pi. So I don't go a steady rotation from point to point to point to point. But I do go from this point a half revolution to there, another half revolution back to there. So I could say, let's start at pi on 3 and add to that multiple half revolutions. Well, a half revolution would just be pi. And that would take care of this and this. Then I could say, what if we started here at this point? That would be 2/3 pi plus half revolution, half revolution, half revolution, multiple half revolutions. And that would take care of this and this. And this is the convention that is typically used. So again, you see n pi, don't say n pi in your head, multiple half revolutions. Okay, now we only have to solve for one revolution of answers. But on the other side, so in some respects, maybe a little bit easier. However, now I've got sines and cosines, and sines and cosines are a good place to be. Oftentimes we change equations or simplify problems into sines and cosines, identities. We go to sines and cosines frequently. But what's better than going to sines and cosines would be to just go to sines or just go to cosines. So I'm going to go ahead and change. I've got some flexibility with sine squared, because we know, this is something that's assumed that you know at this point, sine squared of x plus cosine squared of x equals 1. Sine squared could be replaced by 1 minus cosine squared of x. Okay, so everything in terms of cosines is better than sines and cosines. So if I distribute, I get 2 minus 2 cosine squared x equals 2 plus cosine of x. And it looks pretty clear. I could subtract 2 on both sides. This is an equation. Negative 2 cosine squared of x equals cosine of x. And we're about to enter kind of a dangerous territory here. Excuse me just a second. Just got to get my board oriented a little bit. We're about to enter a dangerous territory here because it is really, really tempting to divide both sides by cosine of x. Let's take a look at something similar. What if I had x squared equals x? And I said, let's divide both sides by x. I get x equals 1. And you say, well, that's right, because 1 squared equals 1. Well, how about instead if I subtracted x on both sides and I factored out an x, I would get x equals 0 or x equals 1. Which of those is correct? Well, of course this is correct. What happened there is when we divided both sides by x, we forgot a pretty important rule in mathematics. You cannot divide both sides by 0. So we lose this solution because now the math gods are telling us, well, x isn't 0. So that would happen here. If we divide both sides of this equation by cosine, we're going to lose some values. So Here's a really good general rule for solving trigonometric equations. If you are ever tempted to divide both sides by a trig function, it is better to group them on one side and then see if we can factor. So I'm going to go ahead and group everything on the right. 0 equals, I'm going to add 2 cosine squared of x to the right side. I'm going to factor out cosine of x. And now I see, okay, now I got factors. Either cosine of x is equal to 0, or cosine of x is equal to subtract 1, divide 2. And I'm going to find out where can that happen. Careful, in one positive revolution. Well, cosine is, of course, x on r. When is x on r equal to 0? X on r is equal to 0 when x is 0. And x is 0 here, and x is 0 down there. And that is pi on 2 and 3/2 pi. And hopefully you're not wondering, why did he not use negative pi on 2? And I would point you up here. That's not what we're looking for. We're looking for one forward revolution's worth of answers. So when is x on r in ratio -1 to 2 when x is negative? That would occur, it would definitely be steeper than that. Try that again. That would occur when x is pretty small. So -1 to 2 here. It would also occur right here, -1 to 2 there. So that would be a 60-degree reference angle, meaning 1 2/60 or 2/3 pi. There would be 3/3 pi, 4/3 pi. Those are our 4 solutions for this equation. Again, why am I not adding on 2n pi's? I'm not looking for all the solutions. I'm only looking for solutions from 0 to 2 pi. Okay, now I've got 3 different trig functions. Well, what's better than having cosine, sines, and tangents would be just to have sines and cosines. So how about cosine of x plus sine of x? One of our basic functions, or basic trig identities, I should say, is a quotient identity that says tangent of x can be written as sine of x on cosine of x. So I get cosine of x plus sine squared of x on cosine of x equals 2. And you may say, what if we multiply both sides by cosine of x here? Well, you got the same kind of danger you had before, in that what if cosine of x is 0? However, if cosine of x is 0, I would suggest we have some problems right there. So you actually could multiply both sides by cosine of x here, but I'm going to go ahead and instead, I'm going to get common denominators here by multiplying this first term by cosine on cosine, making this cosine squared x on cosine x. So I get cosine squared x plus sine squared x on cosine of x is 2. There's our big payoff. Cosine squared plus sine squared is 1. So either, from this, you either get secant of x, the reciprocal of cosine is 2, or you could say cosine of x is 1/2, depending on what you want to work with. I'm going to work with cosine of x 1/2. Well, cosine of x is 1/2 when x on r are in ratio 1 to 2. That is a short value for x, and x is positive. For instance, right here and right here. And the common mistake here, excuse me, would be to say x is, well, that's 60 degrees, 1/3 pi, pi on 3, and then to say, well, x could be negative pi on 3. And that is correct, except negative pi on 3 is not 0 to 2 pi. So this guy should be called 1, 2, 3, 4, 5/3 pi. That's a common mistake, and I suppose teachers, besides besides me end up feeling guilty about that, but I would still take points off. 0 to 2 pi is 0 to 2 pi. Okay, here's something new. We've got a triple angle here. And I'm not used to working with triple angles, and perhaps the worst mistake you could make here in my eyes would be divide both sides by 3 and cancel that 3. You can't cancel this 3. This is not tangent squared times 3 times x. It's tangent squared of 3x. So you don't have a common multiple of 3 on both sides. So I'm just going to do a little a substitution here. I'm going to say a is 3x, and I'm going to work with something I'm more comfortable with. Tangent squared of a is 3, and I'm going to figure out what a should be and see where we can go from there. So that means tangent of a is, careful, plus or minus square root of 3, but I like square root of 3 on 1. That means y to x are in, the y and x values are in ratio of root 3 to 1, positive or negative. Well, that's long y, short x. Seems like we're kind of specializing in this triangle today. That could happen any of these places. And again, we quickly realize those are 60-degree angles. So those are my solutions. But let's take a look. What are we looking for? One revolution? Nope, we're looking for all the solutions. And in addition, have I really solved for a? Not really. So here's what I'm going to, or for x, excuse me, I've really just solved for a. So a is, if I go one revolution, that's 1/3 pi. That would be 2/3 pi. I skip over 3/3 pi to 4/3 pi. 5/3 pi. But I could keep going around, so full revolution back to here. Ran out of room here. 7/3 pi, 8/3 pi, and I usually write 6 of these, and I think you're going to get a good feel for why I do that in this case. Again, we want all solutions, so we're going to have to do this multiple revolution thing. But important, I'm not really interested in what a is. I'm interested in what x is, and so this is really 3x. So to solve for x, I could divide by 3. And I get solutions of pi on 9, 2/9 pi. Did I give myself enough room yet? 4/9 pi, excuse me. 5/9 pi, 7/9 pi, that figures, and 8/9 pi. And those go on and on and on, truthfully, in both directions. So how do I name those? Well, I need to look for a common pattern here, and I see from this term to this term, I go up 1/9 pi, but then I go up 2/9 pi, and then I go up 1/9 pi, and then 2/9, and then 1/9 pi to the next term. But if I'm a little clever with this, I could say, well, let's take a look. From here to here, I go up 3/9 pi. And from here to here, I go up 3/9 pi. So I could start at pi on 9 and add multiple 3/9 or 1/3 pies, multiple 1/3 pies. Likewise, from here to here, I go up 3/9. From here to here, I go up 3/9. So I could also start at 2/9 pi and go up multiple 3/9 pies, or multiple pi on 3s. Okay, so a little tricky, but a nice problem, and we're going to be taking a look at more of those. I'm sure I'll update the website, add some of these. That's my last example for today. So you could look for a part 2 or an extension from this under solving trigonometric equations. Good luck to you. If you're not a member of our class, please feel free. Keep welcome. And if you just happened upon this, you can find a whole assortment of these videos at purpleshirtednerd.com. So welcome and best wishes.